All right. A very good day to you all. Thank you for being here. This is ArbTech in conversation with Ferdinando Samaria on the topic of the next generation of artificial intelligence. Particularly my current obsession of tiny data, and how whether that is something that might be very useful. Notably to arbitration, which is a field known for the paucity of data available in order to field algorithms. We also want to touch upon Mr. Cohen's own obsession with quantum computing, and we're going to talk about machine learning. I am absolutely delighted that Ferdinando Samaria has agreed to be with us. He is someone who has 20 years of experience in investment banking. He has held senior positions in trading and risk management at Credit Suisse and UniCredit. He read electrical and information engineering at Trinity College, Cambridge. He also received a PhD in artificial intelligence. He has published a number of scientific papers in risk management, machine learning, and pattern recognition. He is the author of one of the most widely cited academic works on face recognition. Ferdinando, welcome. And I wanted to say to everyone, because this is, I find that this deadly impressive, that Ferdinando is a world ranked tennis player, and he's just come back from Rafael Nadal's tennis academy, and he has the picture to prove it.
I can certainly prove that is the case. That's me last week in Manacor in Mallorca.
Well, and I don't know where you find the time to do this on top of everything else, but fantastic.
I tell you, I'd be very happy to go back again and put even more time in it.
Excellent. And Ferdinando will be interviewed and in conversation with Paul Cohen, who needs no introduction to most of you, but I will introduce him anyway, because he's not a ranked tennis player, but he's a Star Trek fan. And if he has a picture of that, we'll be happy to see it. And Paul is admitted to practice in New York. He's a barrister in England and Wales. He is based in San Francisco. He represents claimants and respondents in both commercial and investor-state disputes. He is a leader of the Silicon Valley Arbitration and Mediation Center, and he focuses his practice on technology and the representation of technology companies in arbitration. I'm going to let you take it away. Please, we are very much hoping for this to be a session where we're going to learn, but also answer questions that you may have, queries, comments. Please use the chat box to put in your questions. We're going to pick them up and we're going to make sure that they are addressed. I'm going to let Paul and Ferdinando take it away. Thank you.
Thanks, Sophie. Before we got started, Ferdinando was telling us that at the aforementioned tennis academy, they've actually dispensed with umpires. They now have sophisticated cameras and presumably AI or something like it that can actually tell you, if it was in, if it was out, who the point went to. So interesting stuff about how that might be applied with the umpires, as it were, in our field. So Ferdinando, you're obviously an expert in this stuff. This is a fairly, by lawyer standards, a very sophisticated audience. That is not to say that we are, any of us, I don't think, is a techie necessarily, but I think we do understand the basics of AI and machine learning. As far as you know, and we'll home in on arbitration in a moment, but as far as you can tell us, what are the key developments coming up right now in the AI sphere that may impact the process of dispute resolution writ large in the months and years to come?
Okay, well, I think I would start by saying that clearly recently there's been incredible progress at technology level in general. I could give you the standard comparison is with the computer that took mankind to the moon, the Apollo guidance system in 1969. The iPhone 13 that came out this year has got 1 million times more memory. It's 1,500 times faster and weighs 200 times less. So the progress in technology in the wider sense over the last few years has been extraordinary. All these converging technological advances have essentially given us the opportunity to gather a lot of data, way more data than we ever had before. That data requires storage, and now we have incredible amounts of storage. And of course, in order to process it, we require more computational power, which we have as well. Now, so the idea that there is more information out there, we can put it away safely and process it efficiently, has obviously had an impact on artificial intelligence. And we've seen over the last few years in terms of technologies, the advance of the fields of big data in general. And of course, in terms of algorithms, we talk about deep learning as being one of the things that have allowed certain AI applications to progress massively. Now, it's interesting that some of these things, in particular big data, and we can discuss more in detail what, how we've gone from simple neural networks that were trying to solve classification problems with just few items of information, to the fact that now, because we've got so much information and because we can afford extremely powerful models with many, many layers, then you know what, let's put together lots of data, lots of power, and hopefully the neural network will do the right thing. There are applications, and possibly legal arbitration is one of them, and litigation as well, where actually data from a dimensional and number of items point of view is actually not that big at all. And so the question is, what are we going to do about dealing with classification problems where the amount of information available to train your model is actually not very large? Is it possible to come up with new techniques that take advantage of smaller amounts of information? And the answer is there is progress in that area. People talk, okay, AI, like most things in technology, is very fond of catchphrases. So we had big data before, and now that we have a situation where perhaps we can operate with less information, we got something called tiny data. And people are working on the idea that if you don't have very much information, you can still manage to perform classification tasks to a satisfactory degree. It's an interesting idea, and it's not one that is actually entirely new. But if I can give you an example, generally, we like to think that every time you train a machine to learn about something, you need to show that machine a certain number of examples of that something so that the machine can observe, acquire information, calibrate its models, and eventually learn, in quotes, what the key features of the thing that it's trying to learn are. And therefore, you need to show at least some items or examples of the particular thing you want to learn. With tiny data, you have the situation where sometimes the number of training samples actually is smaller than the number of classes that you're trying to classify your objects or whatever it is that you're looking at into. So if I could give you an example, if we have, horses and rhinos as two types of animals, I can show a computer pictures of horses, pictures of rhinos. But then what I can do, I can actually superimpose a set of structural labels on the data and say that perhaps there's an animal which is something in between that has a bit of an element of one and the other, which, for example, could be the unicorn. And therefore, I can teach a system to recognize a unicorn, even though I've actually never shown the system a picture of the unicorn. And the way it does it, it's by mixing and blending two other classes for which it does have examples. Now, that's a rather fascinating idea, but it's one that has been around in a sort of perhaps more abstract way in technology before, because if you look at something called principal component analysis is basically something that looks at a very large sample of information and then decides to cut it down to a very small set of representative axes of that information. And we're talking about, going from thousands of, say, images to actually having probably 4 or 5, which, if you construct the bases of those 4 or 5 correctly, will actually capture the majority of the variance in the sample. So you've gone from having thousands of pictures to only having 4, and then by combining those 4, you are basically able, within a certain degree, to reproduce the thousands that you have compressed. And it's basically not dissimilar from that. Now,
interesting. Sorry, keep going.
I think there's a wider thing, though, that I think I find more interesting, and perhaps I'd like to share with you. In general, we're talking about, artificial intelligence and technology require information to be in digital form in order to be processed and apply its techniques and strategies. And so I think one thing that is fundamental is that, the little information that we may have in some litigation cases or whatever must be fully encoded and digitized so that a machine can start looking at it and making use of it. That's the first thing. And that's really the process of going from essentially, paper to something that may resemble a sort of digital constitution with a collection of digitalized cases. Now, when you do that, and this is already part of the process of soft labeling, perhaps you decide on a data structure which you then fill with the information that you derive from the specific cases. Now, of course, the moment you decide what that data structure should be, you're essentially applying a level of influence from the designer onto the system. However, that has the advantage that if that data structure is sort of theoretically correct, then the power of the little information you got is massively amplified and therefore can lead to much better results. In AI generally, and this is true in the wider sense, we talk about supervised algorithms all the way to completely unsupervised. And really the difference is between the amount of influence that the designer has on the system. You can have unsupervised artificial intelligence algorithms where you basically don't tell the system anything. You just show it lots of things and you say, work out what the distinctive features of what you see are. And the system tries its statistical best and comes up with whatever classification patterns it decides to recognize. At the other end, you've got something completely different, which is actually, I have labeled some of this information for you. I have made some of those classifications and I'm showing them to you as such. Therefore, can you please make sure that you learn that when I say that something represents a certain thing, extract the features that represent that certain thing. That's the other extreme. And then you've got in the middle a mixture where you may have a little bit of labeling or no labeling at all, etc., etc. Now, that is something that where you have limited data can definitely make a difference.
Okay, so let's delve a little deeper into how this might work in the arbitration context. Let's say we have, or we can have, or could have hundreds of thousands, probably millions of examples of case decisions in litigation, not in arbitration, but in litigation. I mean, court cases, there are a dime a dozen. We have loads of those, and we know we're able to classify them one way or another as, this is a contract case where under New York law, this party prevailed under these circumstances because, X, Y, Z. So there's a whole bunch of patterns you'll be able to explore. Maybe you're using, I don't know, you're using principal component analysis, maybe you're using something completely different, but you'll have a bunch of variables and you'll be able to say, this party, these parties, these circumstances, this law, so on and so forth, this was the result. In arbitration, however, as I think you recognize by now, we're only talking about, I don't know, a few thousand published cases, 10,000, or I don't know if maybe someone on the chat actually knows how many published arbitration cases there have been. But there will be highly analogous situations in these arbitrations to some of these litigation cases. How would you, someone says to you, we say to you, okay, Ferdinando, we want to set up essentially some kind of predictive algorithm or some robot arbitrator to tell us how we should rule in these arbitration cases. We only have a few thousand of them, but we have millions of other litigation cases. How do you go about building that using what you've just described?
Okay, so on something like this, you always have two aspects. At the far end, the decision engine, the one that actually generates the final outcome, is inevitably going to be a collection of clauses where the machine checks information, compares information, and then makes decisions. That can be arbitrarily complex. It can be the result of having matched similar situations with cases that have been observed in the past. And importantly, needs to keep an open feedback loop that allows the system to progress and enrich itself every time new information becomes available. For that to work, of course, you need to have the information categorized and placed inside a certain, let's call it, data model. And now that is where things start being a little bit more complex. Your litigation case ultimately is a piece of paper where somebody has done some analysis and come up with a final response. And the question is, how do we translate that piece of paper into the constituent items that fill our data model? So at one extreme, you've got natural language processing. And so you could literally parse the text and try to feed it automatically into your data model. That is a very noisy process. It would require a highly specialized natural language processing engine. And it's one where, again, where the amount of information is not enormous, then you need to make sure that the labeling of that information is as accurate as possible. So my recommendation would be not to do it automatically, which could potentially create more noise on an already small data set, but actually do the translation from document into digital format, sort of driven by a human. That in turn would not only remove some of the noise that you would obviously accumulate by allowing the system to do it automatically, but it would also present the information in the format that the engine that takes the decision and the algorithm at the far end basically understands. Now, that is particularly important. And here, I think we overlap also on something which is really not artificial intelligence, but it's a very sort of popular technology topic, which is blockchain, where people talk about smart contracts, and the idea that essentially legal interactions are actually very structured pieces of information. They're very, a legal contract is very similar to mathematics. You have definitions, you have clauses, you have cause and effect. So it lends itself naturally to being digitized and fed into a system that manages that with a certain degree of automation. And smart contracts, now forgetting the blockchain and what, the security aspects of the blockchain and the trustworthiness and all the rest that comes with it. But in reality, you have a data model which is naturally compatible with the structure of legal language. And so in the litigation case, before we even apply the intelligent algorithm that takes the decision, you do have basic data, which is in a sense natively compatible with a digital model that then feeds into an AI algorithm. So that's one point. And by the way, I'd like also to say that you can extend this from a legal contract all the way actually to the structure of an organization, because an organization, through its internal manuals, operating procedures, and internal organization, is again a sort of legal entity with legal language that describes activities that can be classified into a digital data model. And you can get to the extreme of creating so-called decentralized autonomous organizations, which actually don't have, in a sense, employees or premises, but actually have a set of operating rules that are carried out automatically by a machine. Of course, the interesting thing there is that, oh, and by the way, you can set these things up and finance them through, you know, things like cryptocurrencies and ICOs, where you actually don't even know who the shareholders are. And so one natural question that comes up there is, if something goes wrong, particularly if you have like AI algorithms doing stuff, yeah, and by doing stuff having consequences, if something goes wrong, then, you know, who is legally responsible? What is the legal persona that you're going to deal with? And then specifically, if the mistake, or rather the unwanted consequence, is the result of an AI algorithm, then, especially if it's an unsupervised one, who do you hold accountable? And I think that's actually, in general, in legal terms, quite an interesting question. But going back to your original question, I think the important thing is preparing the information through careful labeling and a strong data model, and then attaching the algorithms at the other end. Once you've done that, even if you have a relatively small data set of litigation examples, it is, you know, you're going to be combining events that you've observed before. You literally count them, and then based on that, you move your probability tree to determine one outcome instead of another.
So you've just bought yourself another visit to talk about what you were just talking about, the liability of algorithms. But let's park that for a moment. In terms of, it sounds as though you're saying that it's perfectly theoretically plausible using, and again, correct them if we're using the wrong terminology, but using essentially some of this tiny data examples, if we have the right classifications, and if we use the right, I assume you're talking about some kind of Bayesian probability, something or other, you can take the small set of arbitration cases and using the, maybe this is via transfer learning, to use another term, but you can correct me if I'm wrong, using the much larger set of variables that you find in litigation cases that are available, you can make your unicorns, as it were. You can say this is the arbitration case which has elements of this litigation case and that other arbitration, and therefore the result is. But is that more or less correct? And,
yes,
and tell me if I'm using the right.
No, and you have used actually some specific terminology there that is obviously used in the area. I think one important thing to say, there's been, because of the technological advances I referred to at the beginning, there has been, in my opinion, excessive enthusiasm for large data sets. And often, many times, perhaps in response to an algorithm that does not perform the way that you desire or converge in the way that you would expect, the solution, because we've got the data, because we've got the storage, and because we've got the computational power, the solution has been, well, perhaps throw a few more training examples, and, you know, maybe the neural network, which had 1 million layers, can have 100 million layers, and so hopefully by shaking it up a bit and recalibrating, maybe the outcome will finally be the one that we desire. And so we've embraced with sort of almost a natural enthusiasm the idea of making everything bigger, to a degree that we've actually, in my opinion, lost most of our understanding of the results that come out from these complex systems. All this to say, and particularly for certain applications like the military, perhaps medicine, investment management for sure, and law as well, when an outcome comes out, the outcome has consequences. And therefore, if something wrong happens, you need to be able to explain where mistakes were made. Now, if you have a multi-layer, multi-dimensional neural network, deep learning network with zillions of inputs to calibrate against, the model is working its magic in a domain that is not the one that we perceive as humans, but it's one of abstract optimization where, by rolling the dice and recalibrating the numbers, the outcome for that specific set of data comes out as the one that you want. But actually, when something goes wrong, you cannot really explain what happened. Lack of explainability is one of the critical points. Now, another advantage of small, tiny data sets is that obviously you run a bit less of that problem because you've had to make the effort of producing soft labels and calibrating the little existing data that you have as well as you can. And therefore you retain more control about what's going on. The other thing is that big data is also a hurdle for medium-sized small operators. Clearly, if you're one of the big tech companies, you have access to infinite data. And therefore it's not a big deal for you to actually calibrate something with tremendously sized training sets. But for other companies, that might not be possible. And therefore, the opportunity of operating in an environment where you don't require huge amounts of data, also because it doesn't exist, possibly opens up to more participants, which in a way, I think is also something positive.
Well, you've anticipated my next line of inquiry, which is in one of the virtues, or the virtue is the wrong word, but one of the ways in which this does work very well, this idea of predictive algorithms or even machine learning and AI deciding these cases, is that essentially we're talking about a fairly binary thing. One side where basically one side prevails and the other side doesn't. So that's fairly easy. But on the question of explainability, what everyone needs in any decision, be it a judicial judgment or an arbitration award, is you do need an explanation. So other than the question of tiny data being easier to explain, as it were, to sort of delve down out of that black box than say big data, what are the ways in which you can get to see the reasoning here? What might be the ways in which the reasoning might be transparent in this kind of in this kind of model? And is there anything down the line that will help make that reasoning more transparent, that machine learning reasoning?
Well, first of all, there are various types of technologies in artificial intelligence that you can adopt, especially when you're dealing with articulated decision processes. So neural networks are relatively binary, or if they're not binary, they may be multi-class in their output, but ultimately they're about putting things in boxes and not really giving you a tremendous amount of visibility about how those decisions came about. Now, the way you can augment that is by subdividing the neural network into structural bits that you understand. So instead of going from the original case information all the way to the final decision, what you actually do is you have a number of intermediate steps where you simplify the structure and allow the system to progress on partial answers as you go along, with the view that you understand all those partial answers because they are essentially capturing a smaller part of the process. Of course, there are entirely alternative systems, like, for example, expert systems. Expert systems are rule-based apparatuses that actually lend themselves to, relatively similar type of tasks. And historically, we've had them, there was an expert system that, acted as a psychiatrist online that you could talk to. And in fact, it was a machine answering back, and he had a set of predefined, previously observed questions or sub-parts of those questions, and he would essentially lead the conversation, mimicking the behavior of a psychologist. Sorry, expert systems possibly could augment this, and then you can have subsections in an expert system where, if a specific complex pattern recognition decision is to be made, then it can rely on a neural network or another classification algorithm. So you can actually mix these technologies to try to get to your final outcome.
Interesting. And I mean, they're so 1980s, aren't they? I mean, expert systems, if I'm not mistaken, are not, they are part of a larger group of AI that's not necessarily even machine learning, or it's not like sort of big data, throw samples at stuff.
It is very 80s, but I will tell you, in my biography, I say that I am the author of one of the most referenced papers in face recognition. So I get every day 5 or 6 emails from the standard platforms, academia and ResearchGate, telling me that my paper and my PhD thesis is still being cited. Now, while I take some degree of personal pride in that, I do have to wonder, how is it possible that something that was written almost 30 years ago is still being considered relevant? And I'm afraid, and on this I'm perhaps a little bit extreme, but whereas we've had massive progress in terms of technology and the available information out there, the artificial intelligence techniques, in my opinion at least, have not really changed structurally from what we had at the beginning of when the discipline was essentially launched. We're working on the edges. We're making certain things a bit better. We're making them certainly a lot bigger, but there is no fundamental challenge to some of the underlying basic models. And so, yes, it is a bit 80s, but in reality, what is there nowadays in terms of really new, challenging, transformational techniques in AI that gives us an edge and wasn't there at the time? And I think the answer is not very much. We certainly have a lot more data. We have more powerful computers, no question about that. But I always find it, so you can go online and you can download libraries of AI machine learning algorithms. I find that quite interesting because it's yet another degree of abstraction. So we have masses and enormous amounts of data, which is quite confusing already. Then we have neural networks, which have got lots of layers and very soon start doing things that you don't really understand. Well, now you don't even have to write them. You actually download them and they're ready-made. So you actually don't even need to go into the details. There's a degree of modularization and abstraction, which puts the final designer in a position of just combining Legos, which is very agile, it's very efficient. But I do have to wonder, what does it do for the understanding that we have of the way these algorithms work? What does it do for, pushing some of these technologies forwards and doing better? Well, the answer is inconclusive, I would say.
Paul, I wonder if I could butt in quickly. Gary Benton has put a very good question in the chat. And Gary, I know you're online. I don't know, rather than me reading your question, I don't know if you wanted to ask it live. Otherwise, I will read it. Please, if you wanted, Gary.
Sophie, please go ahead. You can read it. I have a few typos.
No, you're there. You're there. You
all
asked.
right, fair enough. And good morning to all of you from California. As I said, this is a really fascinating discussion. I wanted to ask a question on what you spoke about a few moments back about combining larger data sets for tiny data sets, and going to Paul's example about litigation and arbitration. And I can see how the relatively larger litigation set from litigation would be useful. I'm just wondering though, how it would work if in the case of arbitration, we have a very small data set. Is there a point where the data set is so small that it can't be useful? And so the example that I gave in my question was the example of the litigation set depends on judges and juries and trial processes, a lot of issues and rules that we don't deal with in arbitration, whereas in arbitration, we have often one or three sort of expert decision makers. And so when you put those two data sets together, how do you avoid ending up with a three-legged unicorn, a solution that is so mutated from either version that it can't guide us as to arbitration? And I'll leave it at that and take my answer in silence.
That's an excellent question, Gary. And I think the answer is, first of all, there's no guarantee that any AI system will not generate a three-legged unicorn. However, what you can do, and in my opinion, what you have to do, is by essentially superimposing as much structure as you can from the point of view of the expert designer onto your system, you need to retain control of the step-by-step decisions that the machine is taking. And that ultimately is your only line of defense. I will give you an example of something unrelated, but which I think is quite fascinating. I've done some work in the medical space, which obviously is one of the sort of areas where AI is becoming popular. And in particular, there was an example of an algorithm that was trying to analyze X-rays of broken bones. So, you know, fractures in legs or arms, wrists, etc., etc. And what happened is that they took a set of images from a specific country in Eastern Europe, and the system was incredibly successful. So a US company decided to try it. They took over some of the data and were running it on the database on which the system had been trained. And the amount of, you know, the rate of success was almost 100%. The system was analyzing X-rays automatically and getting it right every time there was a broken bone, which was obviously very satisfactory. So at one point they decided that after testing it a bit, it was time to try to sort of run a sort of pilot scheme where it was going live, but obviously under high degree of control. And as soon as it went out, the system entirely stopped working completely. As soon as it started getting in real life images, it was failing almost every single time. To cut a long story short, what was happening, and this was based on a rather complex multi-layer neural network that was doing the analysis of the images. The original database on which the system had been trained was using X-rays, where essentially every time that the radiologist identified a broken bone, they would superimpose on the X-ray a small ruler on the bottom side of the picture to provide a scaling, so that, you know, you could check the ruler and compare what you could see in the fracture and get a sense of how big the fracture was. And so every time there was a broken bone, there was a ruler at the bottom of the picture. And so the system had actually learned to recognize the presence of the ruler, not the presence of a broken bone. So when they tried on the pictures in the US without the ruler, the system had absolutely no idea what was a fracture and what wasn't. And I mean, and it took them ages to work out that that was the problem. And again, that's because when you got these systems, you know, if you do not control how information is processed, you've got to remember that the algorithm is not your friend. The algorithm is a very simple-minded entity that has an optimization function And trust me, he will do anything possible to make sure that that optimization function is maximized or minimized, whatever the constraints are. Not because it understands what's going on, just because you said, do the optimization for me, and it will. Now, we must make sure in our tendency to over anthropomorphize everything, we like to think that when he says it's a fracture, it's because it's in the broken bone. No, when it says fracture, it's because it's seen statistically a pattern on all the things that were labeled as fracture that he recognizes on some sort of optimization space. Whether it's the real fracture in the bone or whatever else, that's for the neural network to decide. And so unless you retain control of all the steps of your classification and information management, then the risk is that you will always end up with a three-legged unicorn. Now, of course, if you also have the fact that some of the data may be inherently insufficient, then those checks become all the more relevant, and the expert influence of the person designing the system becomes paramount in importance, absolutely crucial.
I have a question on this. Sorry, Paul, I keep cutting across.
Go ahead.
But since we're on that topic, after that, I promise I won't ask anymore. But whilst we're on that topic, Ferdinando, I've heard of Bayesian AI. Is tiny data the same? Are we relying, because you were talking about expert sort of foundations to the data, and I understand, my understanding of the Bayesian model.
Bayesian is a more generic term, right, that expresses conditionality. So Bayesian is about determining the probability of a certain outcome given something. So generally, a classification system is almost inevitably Bayesian because it gives you the probability of classifying something as a certain outcome given the training data that you've used to generate the learning and the experience for the system. Now, one interesting thing is that there are ways of augmenting tiny data, because interestingly, one way, as we said before, is by superimposing structures that combine the basic elements of that data. So the rhino, the horse, and then the unicorn as a blend of the two. In reality, there is also the possibility of having so-called simulated data, where data that you've not necessarily seen, but given your understanding of structure of that data, then you have generators that also create images that you've not seen before. And I'll give you an example on a slightly unrelated thing, but for example, if you write a program to play chess or drafts or tic-tac-toe or whatever, you can train the system on real matches. So, you know, you go and check when Kasparov played, and you check all his moves, and you show the system zillions of matches that have been played. Or actually, what you do is you write a program that generates random matches, where the system plays by itself using legal moves, i.e. moves that are allowed, but follows some random pattern. But every time a move is done, it remembers what the outcome will be from that move, so that next time it finds itself in that situation, instead of doing the move randomly, it would say, but last time, if I'd done this, I would have won, and therefore it changes the weight of the probabilities. It will do that without having seen that match played in real life, but having it simulated. So, you know, you can have a small number of arbitration cases, but you can create other arbitration cases by simulating situations that are not really happening in real life, by giving your data model, which is always, I always go back to this, the boxes in which you put information is the key, always. Because the moment you design those boxes, you have already passed some information onto the system. You can then fill those boxes with reasonable content, even though you may not have observed it in reality. And so you simulate cases, and then you use them to learn from them. That's
fascinating, because of course that is exactly how the law. Every every legal case is essentially a new chess match with many similarities to old chess matches, but they are, you know, and then you run the analogies, and it sounds as though this would have to be a highly, if and when anyone ever tries this, it's going to have to be a highly supervised system, probably with an expert shell or whatever you call it. You'd need to avoid the problem that Gary was talking about, where, you know, you have the litigation and arbitration of fruits, but you're comparing apples and oranges, as it were. Or you have appenges or orals. Let's I don't know if we're sort of out of time already, actually, and we haven't even got to quantum computing.
I mean, if you wanted to talk a little bit about quantum computing, just briefly before we close, that would be great. Yeah,
that'd be awesome. Yeah. So tell us how quantum computing figures into all this.
Okay. Well, I will start. Okay, quantum computing. First of all, the biggest impact of quantum computing is actually on cryptography first and foremost, and I will talk about that in a minute. But in the context of quantum computing and AI. Quantum computing in general brings to the table a sort of order of magnitude acceleration in speed of execution. So in a way, it could make the problem of having lots of resources and therefore straying off using overly complicated models just because you can't think of anything else, possibly even bigger. With quantum computing, you can really have zillions of layers in a neural network, and the quantum computer will deal with them. So we need to be careful there. But also, the most important thing is that quantum computers, at least at the moment, are not general problem solvers. They are machines that can be programmed to solve specific types of problems only when the problem can be translated into the way information is represented on a quantum computer, so that the quantum computer can take advantage of that. So the most significant algorithm developed in quantum computing is Shor's algorithm, which, you know, Shor is a physicist. In 1994, he came up with an algorithm using quantum computers that allows you to factorize a very large integer. Now that sounds like, and so what? Yeah, you know, factorizing means, you know, if I tell you 15, the factors of 15 are 5 and 3. Okay, that's relatively easy. Now, if I tell you an enormous number with hundreds of digits, and I say this number has got 2 primes that multiply together to generate it, can you find them? That is a very, very complex problem. And it is actually the difficulty in doing that is what keeps together security in the modern world. Digital security is there because we cannot find those 2 factors in a sufficiently fast times. However, if you had a quantum computer with a sufficient number of qubits, then by taking advantage of some of the features of quantum computers, specifically in Shor's algorithm, it's superposition. And superposition is a feature in quantum computers that allows you to have basically multiple items of information exist at the same time. So in normal computers, if you have 3 bits, then you can have 1 of 8 possible numbers. In a quantum computer, if you have 3 qubits, you have all 8 numbers simultaneously. And that, you know, especially as you scale up the number of qubits, that makes a massive difference. Now, if you're clever in taking advantage of the existence of this simultaneous information for the purpose of speeding up your algorithm, then you can do amazing things. Of course, that is a problem, because if you can crack cryptography and security, then, you know, bank accounts, cryptocurrency, medical records, everything falls, literally everything falls apart. For this reason, obviously people are aware, and Shor's algorithm is a published piece of work. The National Institute of Standards and Technology in the US issued a call for applications basically in 2016, asking people out there to propose quantum resistant algorithms for cryptography. And we expect the initial standard that will define these quantum resistant algorithms at the beginning of next year. They got lots of applications. They parsed it down to a smaller number of potential candidates, and they're now down, I believe, to having, I think, about 7 finalists, down from 69, and they will come up with the standard early next year, which is quite reassuring. Clearly, quantum computers will allow AI algorithms to run faster, but we will need to rethink the way our current algorithms are set up, because if you look at the details of Shor's algorithm, it does the factorization of prime numbers in a way which is not natural, but it's actually perfectly suited to a quantum machine. And we will need to apply the same transformation to some of our current algorithms in AI to be able to run them on a quantum machine. Now, interestingly, that might be an opportunity to actually rethink some of the generals. I think one of the side effects of quantum computing is that by having to adapt algorithms to be able to run on quantum machines, we will have to revisit some of the assumptions behind those algorithms. And perhaps, just perhaps, we might be able to identify alternative routes, which will then be substantial progress in AI research, which is, you know, in contrast to what I was saying before, where my thesis is that things have progressed, but not a lot in terms of fundamental models. Quantum computing might give us that opportunity.
Sophie, what do we do? 9:53 in my time. You're muted.
Yes, no, I note that we have another couple of interesting questions in the chat. So maybe we'll address those and then wrap up, if that's okay with you, Paul. Why don't you address them? So Gary put another question along the lines of, what do we say to people who say that AI will replace arbitrators, and what's the answer to the argument that human thinking cannot be replaced? And Stéphanie Faber replies, the issue might be raw data. To replace an arbitrator, one would need a large database of decisions with a relevant set of criteria in relation to facts and applicable law, whereas arbitration decisions are, for the most part, still confidential. And human intervention, she says, is essential. And she also queries what happens to appeals if AI decides, provides decisions, which obviously shows how controversial that topic is, but it is a topic that is raised every single time we talk about technology in arbitration conferences. So Ferdinando, what's your, a scientist's perspective on whether the human mind remains
necessary? I think I'd give you first an economical perspective as an expert. The enthusiasm in the world of banking, insurance, and industry in the wide sense for artificial intelligence, but also for blockchain, cryptocurrencies, or what have you, is, in my opinion, driven primarily by one factor, which is cost reduction. These are all seen as opportunities to compress costs, which in turn inevitably means the objective, the byproduct, the fact that we're going to replace humans is not going to be a byproduct. It's actually the objective. It's the drive. That's why we're doing it. Yeah. So, and I'm not saying whether that's right or wrong. I'm just saying that's why banks find, you know, all of this so exciting, because the moment they see this technology, they think I can get rid of a certain number of people. And that's true across many industries, for sure. I think, interestingly, going back to what Gary was saying before, on top of having something that is broken down into smaller steps that you understand, I think one of the advantages of technology, though, undeniably, is that it goes from a human having to look at an enormous amount of information, which is honestly unmanageable, to actually using the system to filter and cut it down to a manageable set. Now, that's interesting because it will combine the power of the machine doing some of the stuff, but retain some of the human supervision when it actually comes to making that final decision. So we can certainly imagine hybrid systems where specialized humans somewhere along the decision line will step in a much smaller number of them, for sure. So it goes back to the cost analysis I was mentioning before, but certainly, that will be the case. I think artificial intelligence is a loaded term for sure, and it automatically generates sort of images of things that are similar to humans. The algorithms that we're using at the moment have, there's nothing intelligent in them. These are like high throughput calculation engines. If I say to you, is a calculator that does a very complex multiplication an example of artificial intelligence, I think we would all agree that a handheld calculator is not AI. Then if I say, is an AI program that plays drafts an example of AI? Well, in the mid-50s, people, as soon as the AI discipline was defined, people started writing programs to play drafts, and everybody thought, that's AI, that's fantastic, because it's playing by itself. In 2007, a mathematics professor in Canada showed that the game of drafts is actually a solved game. So if you're a top player, it will basically always end up in a draw. Nobody can win. A bit like tic-tac-toe, yeah? Tic-tac-toe, if you know how to play, it's always a draw. Now, therefore, it's not AI at all. It's like just a very complex calculation like the calculator, but it's not AI. So I think I would not venture into, the idea of replacing humans with like for like. We have very powerful calculating machines that will make certain tasks easier. Now, would I step into a self-driven car? As an AI scientist, the answer is almost certainly not. Almost certainly not. Because I know how those models are designed. And remember the example of the ruler in the X-ray. There's going to be an equivalent of that the day that, maybe some rubbish gets blown across the road, the camera in the car sees it. Who knows what it's going to think it is, yeah? In the meanders of the enormous neural networks it's using, it's going to come up with an outcome and a response. It may be a good response or a bad response, but it will not be a response that shows that the system understood, in the sense that we imply as humans, what was going on. Is just as usual the result of an optimization calculation.
Thank you so very much. I think we're going to wrap up. We're out of time. Thank you, Paul, as well for your questions, and everyone for attending. It's been a real fascinating discussion from a very expert point of view. Ferdinando, thank you very much. You may go back to your tennis. We will actually, the recording of this session will be put on social media and LinkedIn. And if everyone wants to spread it, because for those of us who couldn't be here, it will be there for everyone's enjoyment and information. Thank you again, and have a very good rest of your day.
And you, pleasure.
Bye.
Bye-bye.
Bye.